At the Academy for Allied Health, Biomedical Sciences, this is Mr. Smith. We are taking a look here in physics class at Chapter 11, Waves, Waves and Vibrations to be specific. Again, the sections here, I switched things a bit. I started to look at properties of a wave and simple harmonic motion at the beginning. I don't know why they put properties of a wave towards the end. I think it's more important to have it up front. If you're going to be talking about waves, you should learn what a wave is. Remember, go over the anatomy again real quick, and then maybe do the physics. But, you know, to each his own. So I've redesigned it, of course, my way so that this lecture seems to flow a little bit better. We're now going to get into measuring simple harmonic motion. That's what we're going to do now. And then next we'll have wave interactions where we'll talk about standing waves and interference and things of that nature. Okay, so let's first go through the anatomy of a wave. Once we've talked about waves, we've talked about their properties, the two different types, how you can create them with a slinky. Now we want to talk about what they do. Okay, transverse waves are the easiest to talk about with anatomy, although longitudinal waves also will have amplitudes, troughs, crests, all those kinds of things. So the dashed line is the equilibrium position. That is the normal position that our medium will be in. And the wave is the dispersion around it, the disturbance. So what happens in a wave is, remember, it's a disturbance. It's disturbing our medium, which is normally at its equilibrium position. And what it does is it disrupts it and makes it move from one way above, in this case with a transverse wave, above the equilibrium, below the equilibrium, and back and forth, and just always going back and forth, seeking to go back to its equilibrium slot. So here we have points A and F are at the crest of a wave. This is where the wave exhibits maximum amount of positive or upward displacement. This is also where we measure the amplitude, though you can measure the amplitude from the equilibrium to the trough as well. That's where D and I are. They are at the troughs of the wave, which is the bottom, maximum negative or downward displacement. The distance between the dashed line and point A is called the amplitude of the wave. This is maximum displacement that the wave moves away from its equilibrium. Amplitude could be going up, amplitude could be going down. The standard unit for amplitude is the radian or the meter. We will normally use the meter. Radians, remember, if it's less than 15 degrees. From A to F, the distance between two similar points, two crests, two troughs, actually even two equilibrium points is called a wavelength, as long as those two equilibrium points are the same. For example, in this drawing I have in this diagram, from B to G would be considered one wavelength. The wavelength is measured by meters. We do use nanometers mostly because waves are really that small. The waves that we normally talk about, electromagnetic. Sound waves can vary, though. They can be meters in length. This is known also as a wavelength is the length of a wave pulse. Think about what other points wavelengths can be measured. I went over those. Okay, those are things that you want to practice to get to know. Now, what else can we look at? We know that things that repeat have a frequency and a period. So let's think about how we would find the frequency and period of a wave. Again, let's look at amplitude, spring, maximum displacement, pendulum, angle from the equilibrium to the maximum displacement. The SI unit is the radian and meter. So in simple harmonic motion, that's where we find amplitudes. Wave frequency. Frequency measures how often something happens over a certain amount of time. We can measure how many times a pulse passes a fixed point over a given amount of time. This will give us the frequency. Frequency is measured in hertz. So suppose you can wiggle a slinky back and forth and count that 6 waves pass a point in 2 seconds. What would the frequency be? It would be 3 cycles per second. We know this as 3 hertz, Hz, which is cycles per second, s to the negative 1. Now, you're going to get a lot of cross between the two. Certainly when you do the minds on physics, I think you're going to see a lot of s to the negative 1. In the book, you tend to see a lot of s to the negative 1, but then hertz shows up as well. So be careful. They are one and the same. You can use them interchangeably. A wave period, the period is really the inverse of the frequency. It's the same thing as it does with a pendulum. It's the time it takes for one cycle to complete in seconds. It is the reciprocal of the frequency. It's an inverse of the frequency. So if you have the frequency, then you know that's 1 over the period. So invert it, you get the period of the wave. Now, wave speed. A lot of you, when you were working in the lab trying to take a look at mechanical waves, got very much caught up in the idea that you're dealing with light waves. It's only light waves that go at the speed of light. Everything else does not. And you kind of fell back into that equation instead of thinking about what it was you were looking at, which is mechanical waves, or any wave. You need to assume that you don't know its wave speed. Okay? So, to determine how fast it is for a velocity formula, remember it's distance over time. So since we know wavelength and since we can tell period, right? Isn't that with distance of a wave is the wavelength, right? And time is the period. We could have wavelength over period and thus get the velocity, speed of the wave. Yes? Velocity is length of pulse over time of pulse to move past the fixed point. Okay, which can be written like that. Nu, which is what stands for velocity, equals lambda, which is wavelength, over capital T, period. So lambda represents our wavelength, remember? Capital T is period, right? Remember, it's 1 over the frequency. So if you got the frequency, it's good. So then that also means frequency times lambda equals velocity. Hey, wait a minute, I've seen this before. That was with light. Yes, you're absolutely right. Only at that point, instead of having a V, we had C because we knew we were dealing with light, and therefore we were always using 3 times 10 to the 8th. This is more generic. For any wave, speed is determined the same way. Frequency times wavelength. Okay? It is the wave equation. You can use it anywhere. So, a little review. Amplitude is determined by it being maximum displacement from equilibrium. Its standard unit is the meter or the radian. Period, which is time it takes to complete a full cycle, is the second. And frequency, which is the number of cycles or vibrations per unit of time, is in hertz. Now let's talk about the period of a simple pendulum. For a pendulum, finding the period is a little bit different. It's not just finding the frequency. You actually can find it for a pendulum by taking 2 pi, because remember, a pendulum is always moving in an arc portion of a circle. So it's 2 pi times the square root of its length divided by acceleration due to gravity, 9.81. Okay, so it always depends on the length of the string. That's the pendulum. It's independent of the mass. So it doesn't matter how large or how small a mass you have. It's the length of the string that it is attached to that will tell you the period of a simple pendulum. The period does not depend on the mass, right? Okay. For a mass spring system, in other words, you've put a mass on the end of a spring and you want to get the period. Well, that's a little bit different. Now that's 2 pi times the square root of the mass divided by the spring constant. Okay? In this case, it does depend on the mass. A heavier mass will change the period. A lighter mass will also change the period. That should be obvious, though. What the period does not depend upon is length. So any amplitude doesn't really make a difference. Okay? Now, again, this only applies for systems in which the spring obeys Hooke's law, and I will have to say in just about everything we do, we're going to obey Hooke's law. That's it. That's dealing with measuring simple harmonic motion. Now we have a couple of more equations that we can deal with, and that's what will make for a very good quiz coming up. Next, we're going to wrap this up by taking a look at how waves interact. Thank you.